So, today we will come to this last lecture in this module, that is a cylindrical deep drawing. If you consider the cylindrical deep drawing, it is it's a very deep, and that you have a punch which will be applying a force on a blank, and maybe the blank will be deforming. And the blank will be held between this blank holding devices and other things. Okay. This is the blank holder, and we are applying a pressure B here. This is your workpiece material, the blank. And in this, if you just consider this deep drawing where the depth is very large, there is a limit for this, that is the drawing limit is there. So, that when we come to that, you will find that compared to the other small cup and other things. So, here the depth is very large, and this part we can consider consisting of two parts. The one is, see, you have a stretching of a sheet, and another is a drawing an annulus which is inwards. Okay. So, if you just consider it is like this, these are the two things. Actually, we have this tension here, maybe this is T5 we can say. This is one part. So, here at this initial part you will find that the stretch the drawing of an annulus part which is towards the inside, and then okay, it will be moving along, it will be trying to move along this direction, both the sides, and then friction also will come into picture. But whereas the second part is this this stretching of the sheet over a circular path. Okay. So, circular circumferential part around the punch. So, these are the two things, and these two operations are connected to the cylindrical cup wall. So, because of these two things, and the cup wall is not deforming, but it transmits the forces between this both the regions. One is the annular part where it is drawing inwards, and the other is the stretching of the sheet over the circular path. Okay. So, if you just consider the drawing of the flange part, so where it is drawing inwards, so we can say drawing of the flange. So, you can consider that the flange part is a circular part, we are only considering that part, and where see your the flange radius is r0, which is the initial radius, and then okay, maybe this is the ri, the initial internal radius of the flange part, ri, and then okay, you can just take at any arbitrary point r value. Okay. So, if you just look at these conditions, so there are stresses which are there, okay, inside stresses are also there. And if you just look at this the flange of the shell, any part of that can be considered as an annulus part. The stress on the element of radius r, if you just take an element on this flange part at an radius r, okay, so you will find the stresses acting at sigma r plus d sigma r, the radial stresses, and towards this direction it is a sigma r, and then you have the hoop stress, that is the sigma theta which is there, and this is your dr radius, and if you come like this, so this will be your r, and this will be your d theta. So, this is the element, and if you look at the thickness now, you will find that the thickness is something like this, T plus dt, and here you are getting T. Okay. So, these are the the stresses on the element of radius which is taking place. Okay. So, the equilibrium equation when you write for this particular condition for this element, we can just write here as sigma r plus d sigma r, okay, plus into t plus dt into r plus dr into d theta is equal to sigma r t r sigma r t into r d theta plus sigma theta t d r d theta. So, you are expanding and then eliminating that higher order terms and then manipulating it mathematically, you are rearranging it. This reduces to the form d sigma r by dr plus sigma r by r into dt by dr minus sigma theta minus sigma r by r is equal to 0, equation number 1. So, it reduces into this differential equation. So, now when you look at this, you will find that if you take this 2-3 cases, say the radius along a line, if I just take along this line, so you can find out what are the forces at A at the extreme end of the flange, then maybe at B, which is an intermediate between the inner radius and this and the outer radius, and then at C. Okay. At these points, if you just look at the stresses, you will find that at the outer edge, that means at the outer edge of the flange, since it is a free surface, okay, since it is a free surface, your radial component of the stress sigma r is equal to 0. So, you will find that it is a question at the outer surface, the free surface at A, it is a uniaxial compression stress in which sigma theta is equal to your uniaxial flow stress of the material. So, that means current uniaxial flow stress of the material. So, this condition at this point, it will be something like this, okay, and it will be compressive in nature, because if you look at that, when it is drawing inwards, there will be thickening which is taking place. So, so you will find that this is the stresses which are acting, whereas at the point B, you will find that so here the stress state is uniaxial compression, where sigma theta is equal to minus sigma naught. That means, sigma naught is the uniaxial flow stress at that point, okay, at that whatever be the condition, wherever it is there. Now, at some intermediate point B, the radial stress will be equivalent opposite to your hoop stress. Okay. So, that means at this point, if you look at it, you will find that the situation is this is sigma r is tensile, and this will be sigma theta. It will be compressive in nature. Okay. And so, at B, at intermediate point, maybe point B, you will see that sigma r is equal and opposite to your hoop stress sigma theta, where sigma theta is equal to hoop stress and sigma r is the radial stress. And at the inner edge, that is point C, you will find that the radial stress is the maximum. Okay. The radial stress is maximum. So, you will find that from outside towards the inside, the radial stress keeps on increasing from the outer periphery to the inner radius Ri of your this cup. Okay. So, if you just look at the strain diagram at these 3 points, because strain diagram at these 3 points now, assuming Tresca criteria, it will be like this. So, here you are having your what is that, sigma theta, and here it is your radial stress sigma r, okay, sigma 1, sigma 2, that is taking it. You will assume that it is something like this, okay, where this is point A and your strain at point A is equal to epsilon A. Okay, because when it is drawn inwards, there is thickening which is taking place. So, if you just look at this point where the alpha is equal to -1 and beta is equal to -1. No, so in that point, if you like, here it is thinning. If you refer to our earlier this one, and this is thickening. Okay, so here you will get this point B here. Suppose at some intermediate point, these two will be there. So, that is this condition, and maybe so here you may find that this is your epsilon B, and here it may be your epsilon C at some point, and maybe if you just take this as your sigma 0, sorry. This is the instantaneous flow stress of the material. Okay. So, if you so this is your sigma C, epsilon C, not sigma C. So, at the outer edge, the blank will thicken as it deforms because it is in this region, because if you just consider, if you refer to our strain diagram which we have discussed long back, beyond this point on the left of this towards the second quadrant, between the region A to B, the material will be thickening, whereas from B to C, the material will be thinning. Okay. And so, when it reaches to C, there will be maximum thinning will be there. Okay. So, at point C, the inner edge, the sheet will just thin down, and that will be the weakest point. The overall effect is that on one part you are finding at the edge. See, if you find here at this edge, if it is thickening and here it is thinning, the overall area of the flange between the, you will find that it is remaining almost constant, which is a very good approximation. Okay. So, at A, material thickens, at B we can assume no variation in thickness. At C, the material thins, okay, as it deforms. This is during the deformation process which is taking place. So, the overall effect to that is that in drawing, the total area of the material initially in the flange region, it remains constant. Okay. So, there is not much change. So, that is a very good approximation for arriving at some logical conclusion for us, or maybe arriving at some good relationships. Now, if you consider the initial strain increment, when the material is trying to deform and apply the Tresca criteria. So, initial, because you may have to do all this by numerical methods and other things, but if you just consider the initial case and the final case, that will be much simpler for us purpose. So, let us consider the initial strain increment. So, Tresca, applying the Tresca criteria, yield criteria, that is sigma theta minus sigma r is equal to minus sigma 0, okay, where sigma 0 is the uniaxial flow stress. Okay. Now, as the initial thickness is uniform, since the initial thickness of the blank T is equal to T 0, since it is thickness, because this expression is sigma 1 minus sigma 2 is equal to your yield stress. So, that is what the relationship which comes. Okay. So, now when you come to this, if you integrate this equation 1 applying these conditions, the boundary conditions are integrating equation 1 and the boundary conditions are at outside radius r 0, your radial sigma r is equal to 0, and at the inner radius r I, so your sigma r is equal to sigma r I. Okay. So, if you integrate and apply at these boundary conditions, then you can get this relationship sigma r I. I am not going to detailed derivation of that, but you will get it into sigma 0 into log r naught by r 0, that is 1, and sigma theta I is equal to minus of sigma naught minus sigma r I. Okay. So, this you can get it as equation 3. Now, the thing is that for a non-strain hardening material, the radial stress, it is greatest at the beginning, and then it will decrease as the outside radius diminishes. When the radius keeps on decreasing, the radial stress keeps on decreasing. Okay. The greatest stress that the wall of the cup which can withstand is sigma 0. Okay. It will decrease. So, now the thing is that where sigma naught is the uniaxial flow stress. So, more than that, no, it cannot withstand, then it will start deforming. So, if you substitute this, since the maximum, since the greatest stress the material can withstand is sigma 0, we can say that sigma 0, we can say sigma r I, the maximum can be sigma 0. So, if you substitute it into this condition in equation number 3, then we can get this sigma r I is equal to sigma 0. If you substitute that, it will be sigma 0 is equal to minus sigma 0 log r naught by r naught, where small r refers to your log r I, it refers to your inside radius, and capital R naught refers to the radius of the blank. Okay. So, this we can just write like that. So, sigma 0 and sigma 0 will get cancelled. So, log r naught by r I, because this minus sign is there. So, is equal to is equal to 1. So, that means r naught by r I is equal to E, that is approximately 2.72. So, this is the limiting drawing ratio. The limiting drawing ratio r naught by r I is equal to 2.72. This is a rough estimation it will give. But the thing is that this is an overestimate. You may not get that much of a drawing ratio in actual case. There are various reasons to that. One is the effect of strain hardening. So, say A is the effect of strain hardening. As the material is drawn inwards, plastic deformation takes place, and then the stress necessary to draw the flange will keep on increasing, because with the more and more of strain which is happening, say suppose if you take sigma is equal to k epsilon raised to n, maybe in this case, as with more and more of strain happening, your stress will keep on increasing. So, what will happen is with the deformation, the stress necessary for drawing keeps on increasing. Okay. The during the drawing of the flange, the outside radius will decrease at any instant. Okay. So, maybe like if you just look at this case, if this is the thickness. Okay. So, let us say that this is H1 and initially this was so this was R naught. Now it is R, any intermediate point R. Okay. And you will find that here the stresses are acting, that is sigma Ri, and this is your Ri. So, if you consider this at any instant from R0 it has come to R. So, the material has been drawn inside. When the material has been drawn inside, it work hardens, and due to that your stress will be the stress necessary for deformation will keep on increasing. So, that is continuously varying, but for most of the deformation studies we assume for simplicity that we can take an average stress, flow stress. So, average flow stress, like average flow stress sigma naught is considered for simplicity. Okay. So, over the whole flange, and though this deformation is taking place, we found that at the outer extreme edge, as the metal is drawn inwards, thickness will keep on increasing, whereas at this inside radius it keeps on thinning. But we also assume that more or less the area volume of the material is going to remain the same. Okay. So, we can assume that for our analysis, if you assume that the non-homogeneity is avoided, in the thickness is ignored, then equation 3, that means by ignoring non-homogeneity in thickness, then we can write this equation 3 as sigma R I is equal to sigma naught bar into log, say R is at any instant by R I. We can write this. So, it keeps on changing with the R, and then if you just plot that value of R I versus H, the thickness at which it has been drawn. So, sigma R I, you will find that it gradually increases, reaches a maximum value, and then suddenly it decreases to 0. Okay. See, in determining the draw stress, you will find that there are two opposing factors which are coming. One is that as the R becomes smaller and smaller, the stress reduces. Okay. And see that as per this equation, the stress necessary it reduces. But the thing is that at the other side, the opposite is happening, that is the increasing the stress due to strain hardening. So, these are two opposing trends. So, in determining draw stress, the two opposing factors are: 1, as R becomes smaller, as R reduces, the stress reduces, stress necessary reduces. Then as R reduces, strain hardening increases the stress necessary for deformation. Okay. And you will find that okay, these two conditions are there. So, at some this opposite or competing factors are happening. So, it will initially increase to a maximum value and then it further decreases. See, now the thing is that though we mentioned that the drawing limit is there is a limit for that, and it is whatever we have assumed is 2.72 is mainly due to these factors which are coming. Okay. One is we have ignored the effect of friction. So, in the stamping analysis, say B, the effect of friction. First one we consider that strain hardening, second is the effect of friction which is taking place. So, in your stamping analysis, no, we due to sliding around a radius, when it is drawing, when it is sliding around a radius, we arrived at that dt1 by t1 is equal to mu d theta. If you refer back to that, you will find that. So, this can be written in terms of the stress, that means in terms of stress, we can say d sigma phi by d phi is equal to mu d phi. So, we can write this. And if you just look at what is happening when it is moving around to this one, the die, because that it will be coming like this with a thickness. So, here you will find that sigma r I is there, here you will find that sigma phi is there. Okay. The material when you are drawing, it will be moving around this, your die is there. So, this is what is that r d, radius of the die, or maybe I can put r d, radius of the die. Okay. So, considering this, if you just at the this is the condition at the die radius, and if you integrate it, we get this equation sigma phi is equal to sigma r I exponential mu into pi by 2. Okay. So, this is what we will be getting. So, you will find that the friction between the blank holder and the flange will increase the drawing stress. Okay. And it is a reasonable approximation that the blank holder force B will be distributed around the edge of the flange. Okay. Completely when you are applying that, it will be distributed around the flange as the line force of, and we can consider that it is a line force of magnitude B by 2 pi r 0. So, because if you look at that below the flange, this will be maybe it is like this. So, we can say here your frictional forces are there. So, the normal force which is going to act, so that will be, we can consider as B by, it is like a line force of magnitude B by 2 pi r naught, because the total force B, and because it is thickening at the edge only, that thickening is coming. Okay, because there it is thickening, so it will be in contact at the edge. That is one. So, whatever force is there, it is like a line force on the periphery. That is why that we are coming. So, it is B by 2 pi r 0 is the line force which is coming, and per unit length. Okay, so that means the line force per unit length is equal to B by 2 pi r naught. Okay. where B is equal to your the blank holder force. Okay. Now, when you look at this, so there is a friction which is coming into picture. So, at the both the sides, if you look at it, this will be equal to mu B by 2 pi r naught, okay, because 2 mu B and 2 this one is coming into picture. So, we can assume that, okay, this is sorry, if the edge of this flange, if you consider, this will be a line of sigma is equal to mu B by pi r 0 t, where this t is your thickness. Okay. So, that way we can just consider. So, this is your the flange part. Okay. So, this can be expressed as a stress acting on the edge of the flange. That means, so the stress in this direction, the stress, because it is a line force, stress acting on the edge of the flange, that is sigma r at r is equal to r naught is equal to 2 mu B by 2 pi r 0 t. So, that is equal to mu B by 2 pi r naught t. So, this is where B is your blank holder force and T is the thickness, r 0 the initial radius of the your material. Okay. So, both this A and B, what we have, effect of friction as well as the earlier case work hardening, this will increase the stress required to draw the flange. Okay. So, integrating equation 4, we can get with the boundary condition of equation 7, we can write the expression for the drawing stress. Is equal to, and you are using the average flow stress, log r naught by r I plus mu B by pi r naught t. And if you apply this to equation 7, equation 6, we will get the side wall stress sigma phi is equal to, we can finally express it in this. I am not going into the detailed derivation, but we can get it sigma naught bar log r naught by r I plus mu B by pi r naught t into exponential mu pi by 2, where this is an efficiency factor which takes care of bending and unbending. Due to that, no work hardening will take place. At the same time, friction also will come in, okay, over the die. So, that is what we are going to get it. Okay. Now, there are some cases where we can discuss about the wall ironing, because after deep drawing you may give an ironing process, you may apply on that, so that it becomes, its thickness will get reduced, and then you get a very uniform thickness with a good surface quality also. So, that process is called as ironing. So, wall ironing of deep drawn cups. So, if you look into that, this is a process, but I am not okay. I will explain that. See, if okay, see, suppose this was the material, and by ironing you found that the thickness has reduced. Okay, we have to assume that this is uniform thickness. I can draw only up to this way. So, here you have a die like this. Okay. So, this is the ironing die. So, if you just really look at this part, see, it will be like this. The forces will be like this. You are having this normal force Q here. So, these two will be different, because the frictional force at the punch workpiece material and the die workpiece material will be different. Okay. So, and this is your thickness, we can say that this is T2, okay, and initial thickness, let us say it is T1. Okay. So, these are the forces which are going to come into picture. So, you will find that when the punch moves down, it moves down with the velocity of the punch, that is Vp. Whereas, it may not be the same here, the material may not be moving with the same velocity here. So, that means V1 at the initial stage will not be the same as the output velocity. Output velocity will remain will be a constant as the punch velocity, but here it will be different, it will be less than that. So, as the punch must remain in contact with the base of the cup, velocity of the material as it exits the die is Vp, velocity of the material as it exits the die is equal to Vp, and so that is equal to the punch velocity, we can say punch velocity. But during the ironing there is no change in the volume, volume remains constant, but the thickness at the end ray is higher. The thickness T1 is greater than thickness T2. Okay. So, the rate at which, because of this, the rate at which the material enters into the deformation zone, okay, that should be the same as the rate at which it leaves the die. Okay. So, for that case, what happens is that because the velocity of the material at the exit of the die is Vp, the velocity at the inlet to the deformation zone will be lower than Vp. Okay. So, hence, okay, we can say that since the volume rate of metal which enters into the deformation zone is equal to that which exits the die. Hence, the V I inlet velocity of material V I will be less than V P. Okay. So, since the constant volume relationship is maintained, you can say that if you write this equation 2 pi R I T I into V I is equal to 2 pi R I into T 1. Okay, this is T 1 V 1 we can say T 2 V P. So, from this we will find that V 1 is equal to V P into say T 2 by T 1. So, that we are getting. So, now the punch is moving down faster than the incoming material, and the friction force between the punch and the material is downward. So, that is one case. So, if you look at that, the punch is moving down and the friction force is also there. So, that will be moving down at the punch material interface, but it will be moving down. But if you look at that frictional force at the die and the punch, it will be upward. It is in the opposite direction, because more material is coming and filling up that area. So, it will always have a what you call it as backward flow of material, and okay, due to that your frictional force will be in the opposite direction. Okay. So, initially the friction at the die at the punch and the material, basically at this region, so that is equal to mu p. Since it is mu p is downward, it will be assisting the deformation process. Whereas in this case, you will see that this friction will be downward mu d, that will be moving upward, not downward. It will be moving upward. So, that will be opposing the deformation process. So, for this case, because mu p, that is the frictional force at the punch metal interface, is assisting the deformation process. If you have a higher frictional force, then it will be very useful. So, many times now people make increase the surface area of the punch surface, but of course, you cannot increase too much high, because you may face problem in removing it also. So, if the surface whereas at the die material interface, your friction should be less. For that, people may add large amount of lubricants at their surface, so that the resistance will be reduced in this. Okay. So, it is advantageous to have high punch side friction at mu p. Now, if you assume that the material behaves in a, assuming the material your blank is rigid, perfectly plastic. Rigid perfectly plastic means it is this way. Okay. So, that means sigma f is equal to your yield strength sigma y naught uniaxial yield strength is it remains a constant and no work hardening if it is there. And if you apply the Tresca criteria, Tresca yield criteria, and the true thickness stress, through thickness stress at entry, where axial stress is equal to 0, you can write that Q is equal to minus sigma t is equal to sigma 0. Okay. So, that means at the exit the axial stress is less than sigma 0 to ensure deformation occurs only inside the die. Okay. So, as shown in figure, you can also come out with certain cases like the axial stress. If you just draw this figure, so this is T0, this is T2, and this is delta T, the change in the thickness. Okay. So, you will see that okay, this is gamma, and you can say that the forces which are acting also you can write this, what is this dimensions, delta T by tan gamma. So, if you just take this delta T by sin gamma, okay. So, in this case, no, if you look at the forces which are acting on that, so it will be say you have the frictional force here, the normal force here. Okay. So, this is similarly you have this normal force here, and you have the frictional force in this. Okay. So, this is the die side, here die side, and here it is punch side. Okay. So, if you just look at that here at the top it is 0, whereas at the down you will see that m into sigma naught into T2. Okay. So, similarly here you will find that shear stress is mu d, where the stress frictional stress at the die metal interface into q bar into delta T by sin gamma, and here it is equal to mu p into q bar into delta T by tan mu tan gamma. Okay, tan gamma, and here you will find that this is punch side. So, here this will be q bar Avrai flow stress, q bar is basically is equal to into delta T by tan gamma, this is die side, and here it is equal to q bar into delta T by sin gamma. Okay, you are getting. So, you will find that q is equal to minus sigma T is equal to sigma 0. Okay. So, if you assume that through thickness T sigma T, the stress through thickness stress sigma T is equal to sigma 0 minus m sigma 0. Okay. Because the axial stress sigma phi is equal to m sigma 0, where m is less than 1. So, at the exit you will find that q is equal to minus sigma T, that is equal to sigma 0 into 1 minus m. Okay. So, the average contact pressure, if you take it, the average contact pressure q bar is equal to sigma 0 into 1 plus 1 minus m by 2. So, that is equal to sigma 0 into 1 minus m by 2. Now, if you take the equilibrium forces in the vertical direction, okay, so taking equilibrium forces, of forces in the vertical direction on this element, what we have shown, is equal to m into sigma 0 T2 plus mu p into q bar mu p into q bar into delta t by tan gamma is equal to mu d q bar delta t by sin gamma into cos gamma plus q bar into delta t by sin gamma into cos gamma. Now, substituting this 12 in 13 and then do a mathematical simplification and considering the fact that the limiting condition, for the limiting condition the maximum thickness reduction occurs when m is equal to 1 using 12 and 13, we can get delta t by T2, the maximum, is equal to 1 minus mu p minus mu d by tan gamma. So, this is what you will be getting. So, you can just do this by having the surface quality, okay, surface phenomena of the punch and the die, so that now your friction can be changed accordingly, and then you can have the maximum reduction based on this mu p and mu d, and what is this angle at which it is going to take the die angle, what is that, you can find it out. Okay. So, that is the maximum the limiting condition for maximum thickness reduction. So, that way you can get it. Okay. Yeah.